During this lecture, we will be discussing another part of general linear model, namely factor analysis. An example of the situation when we can apply this analysis is the following. Imagine that we want to determine the depression level in a patient. The problem is that the depression level is not very well defined quantity that can be somehow directly measured. So we have first to construct this index of depression of, I don't know, level, the measurement of depression level, whatever we want to call it, examining a group of patients that we know that suffer from depression and that have symptoms that can be directly observed and quantified. For example, we know that depression can cause sleep disorders, and this is something that we can quantify. And depression can cause symptoms like lack of energy, sadness, instances of unsocial behavior, etc. All those traits can be encoded in a number of variables. Let us call those variables x1 up to xp. These variables can be measured. And our model says the following. Each of the variables is composed of some parts. First is a number, as we will see in a moment. This is the expectation value of the variable, but just a number, one number for each variable. Then there is the component related to depression, so there is some coefficient lambda, and this unknown as for now factor being the depression level. And of course, each symptom can be related to more than just depression. Therefore, there is also an error. The assumptions are that there is no correlation between error and the depression level, and there is no correlation between errors for different measured quantities. So if alpha is different from beta, then this correlation is equal to 0. So this is the simplest model that we start with doing factor analysis. Of course, there may be more factors than just one. If we have more factors, maybe before we pass to multiple factors, let us try to interpret the coefficients. For example, if we calculate the correlation between x alpha and the factor, so using the model, we put this model here, and we get correlation between the value of x alpha, which is mu alpha plus lambda alpha f plus epsilon alpha. And then using the assumptions, we see that, of course, this mu alpha doesn't matter much because it is constant. Therefore, we have lambda alpha times correlation between f and f, which is a variance of f, and then a correlation between the error and f, which is assumed to be 0. Usually, we also assume that the factor f is normalized, which means that the variance of this factor is equal to 1. And of course, we assume also that mean value of f is equal to 0, not 1, at 0, which means that the only place when this expectation value appears is just here. Yeah, so this is the expectation value, and the rest of the variables, I mean variable f and variable epsilon, have expectation values equal to 0. So it means roughly that f is a standardized variable. So assuming that we have chosen this factor to be standardized, we get the interpretation of alpha, which is not alpha but lambda, sorry, the interpretation of lambda to be the value of the correlation between the factor and our variable x. And now we can pass to the case with multiple factors, and the model can also accommodate such a situation. Let us think of the following example. There are theories about human intelligence that tell us that this intelligence, whatever it is, comes in various aspects that people can possess in different degrees. These aspects of intelligence can be verbal intelligence, numerical intelligence, spatial intelligence, emotional intelligence. There are several of them. And in those various aspects of intelligence can be measured via different tests. But usually it is not like that the particular test measures just one type of intelligence. So again, we have results of tests that are those x alphas, and we have factors that are supposed to be different aspects of intelligence. So factors, aspects of intelligence. Let us denote them by FB or F capital A. And then alpha belongs to the set of indices from 1 to p, number of tests, and factors. So A belongs to the set of natural numbers from 1 to m. So we have m factors and p tests. And now our model says that each result of the test has, of course, its expectation value, and then can be expressed as a linear combination of those intelligence aspects. So there is a matrix here, lambda A alpha F FA. And as usual, we sum up over indices that appear twice, once up, once down. So unexpected appearance of Einstein's summation convention in statistics. And there are, of course, errors. And we have, again, the set of assumptions. We assume that expectation value of each error variable is 0, that different errors are not correlated. So this is 0 if alpha is different from beta. And also that errors are not correlated with factors. So this is also 0. And we will assume that factors are chosen in such a way that their expectation value is equal to 0. And moreover, they are standardized and uncorrelated between themselves. So we can write that the correlation of FA and FB is just delta AB. So it is 1 when it is just variance, and it is 0 if we have two different indices, which means two different factors. And from then, of course, it again follows that the expectation value of x alpha is this number mu alpha associated to each x alpha. Usually, especially when those test results are measured on the different scales, usually we, before performing the analysis, we standardize them. And then this mu alpha becomes 0, and also variance of each variable x alpha becomes 1. If all the tests are measured on the same scale or on very similar scales, then we can forget about standardizing and work on the raw data without any transformation. However, usually we transform those data. Okay, so to see really what's what, let us write this equation, this model in a matrix form. So we have a vector of variables, x1, x2, up to xp, and it is supposed to be some constant vector plus a matrix. This is the lambda matrix, and the lambda matrix acts on factors, which there are m of them, and this means that we have here m columns and p rows, and of course we have not equals but plus, and we have here those errors, epsilon p. So this crucial in our analysis lambda matrix, which is called the matrix of loadings, it is the matrix that has p rows and m columns. Other names that one can encounter in the literature are factors are sometimes called common factors, and those epsilons are called specific factors. That means that all those lambdas, all those x's can be divided to the part which is common and the part which is specific. So this common part somehow summarizes all those x's together, and the error is specific to each variable. Again, we can look at the variance of x alpha. And if the assumptions are satisfied, which means that factors are not correlated with errors, and also factors are not correlated between themselves, we can split this variance into the part depending only on factors and the part that is that depends on error. And of course, we would like, if the model is good, then this is small and this is big. Moreover, then we can still apply what we know about the behavior of variance, and we can write it like that. This is the sum. If f's are not correlated, then this is the sum over b of lambda of lambda b alpha squared times variance of f b, which is assumed to be equal to 1. Therefore, we have the following final form. The variance of each test result is composed of the sum of squared matrix elements of the matrix lambda and the variance of the error. And this thing is called commonality for x alpha. And we assume this commonality to be rather big. It is used to measure the performance of the model, since it says how much of the whole variance is explained, of the whole variance of variable x alpha is explained by the model. So sometimes we also use explicitly the percentage. If we didn't standardize our variables x alpha from the very beginning, then to measure the performance of the test, we have to somehow normalize this commonality, and then we use this commonality as a percentage of the total of the variance of variable x alpha. So this will be the sum over b lambda b alpha squared divided by the variance of x alpha. And we would like this number to be as close to 1 as possible. Then it means that error is small. Another calculation that we can do here is looking at the whole correlation matrix of the data. So let us denote this matrix by sigma. So sigma alpha beta is the correlation between x alpha and x beta. And again, according to the model, we can put x alpha as a combination of factors and errors, the same for x beta. So the sigma alpha beta is the correlation between, we forget mu's because they do not influence the correlation. So here we will have lambda a alpha f a plus epsilon alpha, and here lambda b beta f b plus epsilon beta. And again, if we use the assumptions about f's and assumptions about epsilons, what we get is the following. This will be the sum over A and B, lambda A alpha, lambda B beta, and the covariance between F A, F B, and the covariance between epsilon alpha, epsilon beta. So this is the matrix element of the covariance matrix of errors. So let us denote this somehow. This is delta AB, which means that here we in fact have matrix lambda times matrix lambda transposed, and the alpha beta matrix element. Therefore, the matrix sigma can be composed from lambda transposed plus psi, and this comes from errors, and in the ideal situation this matrix should be diagonal. And this is another way of measuring how well our model performs, because in true situation, in estimation, usually this matrix of errors is not diagonal. However, we wanted to have off diagonal elements very small, because then it means that our model performs well. Note that in this presentation here, and this splitting between in this splitting of the correlation matrix into the part that comes from factors and the part that comes from errors, the diagonal part, there is some freedom of definition of those factors, because if we, for example, apply rotation to once defined factors, so imagine that we have this vector of factors f1 up to fm, and we replace, so let us call it f, and we replaced this by some f tilde, which is the result of acting by some orthogonal matrix on this f. This is p times, not p times p, m times m. This is m times m orthogonal matrix. Then when we calculate lambda tilde and lambda tilde transposed, we will see that this is exactly the same as lambda transposed. Because if we keep roughly the same situation, so x alpha now is mu alpha, which is as usual, and then there is lambda tilde f tilde plus errors as before. It means that, and this is of course the same as mu alpha plus lambda f plus epsilon alpha. So this means that this lambda tilde equals lambda times O, matrix O to the power minus 1, and since it's orthogonal matrix, this is the same as transposed. Yeah, and then if we calculate lambda transposed, we will have lambda without tilde, O transposed, then lambda without tilde, O transposed, and we see that this is lambda, O transposed, O, lambda transposed, this is 1. Therefore, this is really lambda transposed. It seems that there is a significant freedom in the definition of those factors that keeps the splitting of the correlation matrix into the part assigned to errors and this part associated to factors, that keeps it unchanged. And this means that once we define our factors somehow, because the process of extracting factors is just another matter. I mean, we will be doing an example in a moment. So when we do it, we can then adjust those factors applying rotation. And again, there are several methods of rotation. Usually the rotation is done in order to get factors that are more easily interpreted. Okay, so this is the model, and now the problem is that what we want to do, we want to find those factors somehow practically. There are several methods of extracting factors from the data, and since we are now accustomed to principal component analysis, we will discuss the procedure of extracting factors using principal components. So essentially, some of the principal components can be used as factors. They can also be additionally rotated. Okay, so there is one thing that I forgot to mention here. exactly as in the case of one factor, we can calculate the correlation between x alpha and f a, so the correlation between the measured quantities and the factors, and it is easy to obtain that this is exactly the matrix element lambda a alpha. So this is this matrix of loadings is in fact matrix of the correlation between initial variables and our factors, which can help us in interpreting the factors that we obtain. So now we are passing to principal component analysis as a source of factors, so PCA method. We start as in the PCA method. We start with sigma, which is a correlation matrix. Initially, it is a covariance matrix. But for standardized variables, it is the same as correlation matrix. So if we want to work with standardized variables, then the correlation matrix is okay. We find eigenvectors and eigenvalues. Since this covariance or correlation matrix is symmetric and positively defined, it has positive eigenvalues and orthogonal eigenvectors. Usually we choose eigenvectors normalized. So our eigenvalues will be now denoted by small lambda. We have lambda 1 up to lambda p eigenvalues. Of sigma, and we order them in such a way that the first is the biggest. So this is lambda 1, which is greater than lambda 2, and so on up to lambda p, which is the smallest of them. And our eigenvectors will be defined by capital E alpha. These are eigenvectors corresponding to those lambdas, and we want them to be normalized. So each eigenvector is a combination of initial variables, and this normalization refers to the canonical scalar product in Rp, because the space we live on, I mean this, each x1 up to xp, this belongs to Rp, yeah, and each E alpha also belongs to Rp. Those initial variables x are treated as orthogonal in Rp because they correspond to the canonical basis on Rp. And also those E alphas can be taken normalized with respect to the scalar product in Rp. This means that we have the relation between initial values and initial variables and those E alphas is by means of a matrix which is again orthogonal. Because it transforms the basis, the canonical basis, which is orthogonal, to the basis of eigenvectors, which, according to spectral theorem, also are orthogonal. Orthogonal, it means that if we want to have an inverse, this is the same that transpose. Okay, so factors are related to eigenvectors, but they are not exactly eigenvectors because factors should be variables with variance equal to 1. And as constructed, variance of each variable E alpha equals lambda alpha. So what we have is the square of E alpha equal to lambda alpha. Because this is the diagonalized correlation matrix, yes? So on the diagonal we have variances of variables. Therefore, we define our factors, F alpha. This is a candidate for a factor. As E alpha divided by the square root of the appropriate lambda alpha. And now those factors are uncorrelated and they are normalized in the sense that they have variance equal to 1. Okay, so let us now determine loadings of our factors. Loadings are correlations or covariances between initial values, so initial variables, and our factors. So by definition we have here the inverse of A, say gamma alpha E gamma, with the factor, and the factor is 1 over the square root of the eigenvalue times E beta. And again we use the properties of the covariance, and what we have is those matrix elements times 1 over the square root of lambda beta, and the correlation between E gamma and E beta. And this thing equals lambda beta times delta. Because those eigenvectors are eigenvectors, therefore they are uncorrelated as statistical variables. Okay, and then we go forward with our calculations. And we see that what we get is A to the minus 1. We apply delta in the sum, and we have beta alpha here, and the square root of lambda beta. So loadings come from, in fact, coefficients of eigenvectors, because this A matrix are coefficients of eigenvectors in the standard basis in Rp. So here we have coefficients of eigenvectors multiplied by square root of lambda b. And this is true for all the factors. Now we have p factors, which is definitely too much. And we have to apply some procedure of selecting smaller number of factors. In the literature, there are three procedures that we can use. So first procedure says that, or maybe I should write here that this is about selecting factors. So the first procedure of selecting factors is the first procedure says that we take as many of the factors as is needed to get the percentage of variance explained by the model greater than 0.8. So the percentage of variance explained in the model can be expressed in the following form. We take the sum of all eigenvalues from 1 to m. The number m is to be determined. So we sum those eigenvalues and we divide it by the trace of the correlation matrix or covariance matrix, depending from which matrix we start, which is the total variance present in the model. And we want this to be greater than 0.8. And the number m should be the smallest number that assures that we get this inequality. The second procedure says that we take factors with eigenvalues which are at least 1. This is easy to say when we start from standardized x's. Then the trace of the matrix is equal to the number of measurements, number of x's, so then the trace equals p. And then then we take factors with eigenvalues greater than 1. So take factors with eigenvalues greater than 1. If we started with variables that were not standardized, then we should select factors with eigenvalues that are greater than the trace of sigma divided by p. So this is this is then instead of 1. And there is the third procedure, which is based on the plot of eigenvalues. We can plot them. Here will be the number up to p. And remember that we have ordered our eigenvalues from the largest to the smallest. So the plot should look somehow like that. And sometimes it happens that we have so-called elbow in the plot. So we have this elbow here. We go down, down, and then again down, but not so fast. So this is this elbow in the plot. And the rule says that we take all the factors before the elbow. So in this case, 3. So which procedure we choose is up to us. We will soon do some examples and see what are the differences and what are really the possibilities, which rule to apply. Okay, then to assess the quality of the model, we can again look at 3 possible measurements. Quality of the model. First, we can look at commonalities. So those numbers H alpha defined before. This was sum of squared matrix elements for from the loading matrix. We sum over all factors divided by the variance of X alpha. And if all the commonalities are close to 1, then our model is good. So we expect H alpha to be close to 1. The second way to assess the quality of the model is to check the fraction of total variance explained by the model, which means that we take the sum of eigenvalues corresponding to chosen factors and again divided by the trace of our initial covariance matrix, and again we want this to be as close to 1 as possible. Close to 1 means the model is good. Because this says how much of the total variance is explained by the model. And again, the third possibility is to look at correlation matrix of errors or covariance matrix of errors. Psi alpha beta. This is this psi. And this psi is covariance matrix minus matrix of loadings multiplied by its transpose. In the perfect model, this matrix is diagonal, and if it usually in practice it isn't, and the model is good if off diagonal elements are small. Of diagonal elements small, this means the model is good. So this is all about the theory. In the next recording we will apply this theory to one example, and then there will be 2 other videos about additional rotations that we can apply to factors. The factors that we get from principal component analysis are determined by the sigma matrix. There are eigenvectors of this matrix. However, as we have seen, from the point of view of factor analysis, we can rotate them to enhance somehow the loading matrix, to make the components more correlated to the particular variables from our measurements, from our set of x's. This helps in interpreting the factors. There are several possibilities how to do it, and we will discuss in detail the procedure which is most common and which is called Varimax procedure of rotating factors. But this is the subject for the next recording.